Okay? It's okay if you did not bring, alright? All of you should download this from Moodle and give it a try. So in this tutorial exercise 1, it's also very straightforward. You are given 4 different waveforms. Okay? Based on your matriculation number, alright? You can calculate your maximum voltages, the rise time, the fall time, etc. Let's just go through one of this, okay? Let's say we go through this, sinusoid. Okay. Can everybody see? Alright. First of all, I hope you guys know what it means by peak to peak, right? Yes? Okay? In this case, your peak to peak voltage is 10 volts. And you have an offset of -4. Okay? Are you able to calculate the average voltage and the RMS voltage? Okay? You should know this because this has been covered in the introduction slides. Alright? The average value of the waveform will just be the DC offset because it's sinusoidal waveform. Okay? The root mean square value of the sinusoidal waveform with a peak amplitude A volts and DC offset B volts is given by this. Okay? And the peak voltage that you have is just the peak to peak voltage divided by 2. So now you have a sinusoidal waveform A sine omega t plus a DC offset B. What you do to calculate root mean square is you do a square. Okay, we've gone through this before. Okay, do your integration. And then you end up with a root mean square voltage. Yeah.
Yes, sir.
Okay, this is very straightforward, a sinusoidal waveform, right? Now, can you do this?
No.
Okay, how do you actually do this? How do you calculate the average voltage and the RMS voltage? Alright, for those who can see, this is more of like trapezoidal shape.
Oh, tak. Yang tu kan post experiment.
Okay. Firstly, you need to be able to correctly describe the way the waveform changes with time. Okay? So, meaning you need to come up with a mathematical representation for your voltage V. What you get in terms of voltage function is Vt is equals to V on plus, what is this slope here? V off minus V on over T on times T. Okay? But this is only valid for T from 0 to T on. Okay, you must be very careful with this. Alright? So if you know this, okay, you know that for calculating root mean square, you need to have a 1 over T integrate from 0 to T on only, because this is only valid from 0 to T on, right? And then you do a V square T dt. Okay? roots, mean, square. Okay, there will be a, for VRMS there's a square root, there's a mean, meaning you divide by a period, and then a square, meaning your V squared. Okay, if you do this, expand out and simplify, you will end up with this expression. Okay, and then how do you calculate average? Average is 1 over t, integrate from 0 to t on vt dt. Okay, same thing, you expand and then you simplify. Very straightforward, right? Okay, all of you have to know this. Okay? Alright, so if everybody is comfortable with doing all this integration and simplification, we have a bit more time left. Shall we move on to the part 2 of switch mode power supply? Okay? Don't worry about it, I'll just go a bit more slowly. Okay? So that for your makeup lecture on Friday, I will give you all some more time for breaks. Alright? Be reminded that there's a makeup lecture on Friday at 11.
Okay.
Okay, for switchboard part 2, there's a slide given to you just to explain, to share with you what's a typical DC to DC converter application. So for example, in DC motor drives in robotics, okay, you need to step down the voltage to power sensors that require very low voltages. Okay, there's also power factor correction, which will be covered in a later lecture, and active filters that will require a conversion in voltage.
Robotics, yes.
Alright, there's a small diagram here just to illustrate to you how a DC to DC converter is used in real life. Okay, you can see that there's a solar array. Okay, this is 1,300 watts in 9 panels. So what do you get from a solar panel? Do you get AC or DC power?
DC.
Ah, okay, for a solar panel you get DC power. And the way to control the power to ensure that you get maximum power is by using a maximum power point tracker. Alright? Okay, and this DC power that you get from the solar panel will be stored in a battery pack. Okay, in the occasion that it rains or whatsoever, you can actually directly get the energy from the battery. Alright? And if you all know, if you all understand battery, does it give you AC output or DC output? DC, okay? And this DC output will be powered to a DC to DC converter, which will give you either 5 volts or 12 volts output, depending on what components you wish to power. So if you want to power accessories like fans or horns or signal left, signal right, this is usually 5 volts. Okay? Whereas for radio modem and microprocessor, the microprocessor which controls your cruise control, your 4-wheel steering system, and your driver display, these are usually 12 volts. Okay, so this is the way you use a DC to DC converter. Alright? So, previously we already covered a step-down converter. Now, we will talk about a step-up converter. Alright? Remember that we talked about a step-up, we say that the output voltage will be greater than the input voltage. Okay, I hope you guys can see that there's now a difference in the circuit arrangement. Right? Previously the switch was here, the diode was here, the inductor was here, capacitor and resistor. Now it's all different. Okay? You have an inductor here, your switch connected in parallel to your power supply. Okay, you have a diode here, and the same goes to the capacitor and the resistor. Alright? Okay, if you can remember, a step-up converter, which is a boost converter, is used to increase the output voltage above the input voltage. Similarly, in the case of a boost converter, we also assume that it operates in continuous mode, meaning there's always current in the inductor. Alright? If you ignore the switch for a moment and you examine this circuit, you can see that in steady state, the output voltage is connected to the input voltage via the inductor and the diode. Right? If this switch is left open, But what do? We already said that we ignore the diode drop. Diode voltage drop. Okay? Alright, so now if you want to close the switch, what will happen? Once you close the switch, any voltage on this capacitor C will ensure that the diode is reverse bias. Okay, why? Can you see that once you close the switch, this end of the diode is connected to the negative terminal, whereas this end is still positive. Okay, if this is negative, this is positive, this is reverse bias. Alright? Therefore, the output circuit is disconnected from the input when the switch is closed. Okay? And the inductor is connected directly to your V-in supply. Hence, the current will start to build up in the inductor and energy is being stored in its magnetic field. So during this phase, your voltage in the inductor is equals to V-in. Okay, but note that it's pointing in this direction. Alright. What happens if the switch is now open? Okay, when the switch is open, remember that previously there was a magnetic field in the inductor, right? This inductor wants to maintain the current flow. And with the supply side of the inductor, which is still held at V-in, what will happen is that the potential on this side will try to rise until the diode starts to conduct. Okay, if you ignore the voltage drop across this diode, this end is essentially your V out. Okay, so this is V in, this is V out. Alright, hence your inductor voltage during this phase is just the difference between your input voltage and your output voltage. Alright, so you get V inductor is equals to V out minus V in with a negative sign. Why? Because it's now a opposite direction as compared to the previous case. Okay, previously you have your voltage of inductor in this direction. Now it has changed. Alright, so that's why you have a negative sign. Okay, so in this case, the charged inductor will slowly discharge and energy in this magnetic field will fall, which is illustrated by this waveform. Alright? Okay, so this is opening and closing of the switch, and the inductor voltage will fluctuate from V in to minus V out minus V in, and the inductor current is like this.